Okay, this is the last section for the semester. It is 12.4, the normal distribution. And I want to introduce it by talking about the normal distribution. And if you recall, we had a data set. We had a data set, and if it was normally distributed, then if you have your mean here, so your mean, one standard deviation from the mean. So let's call this 1 SD, 1 SD to the right or to the left of the mean, that would cover a certain percentage of your data. And what that actually is that coverage is 68% of your data. Okay? I think last class I said like 70 or 75. That wasn't right. But that's the exact amount, 68%, if your data set is normally distributed. Within 2 standard deviations, so if you go 2 standard deviations out, so you go 1 more, that's not quite, try to get it a little bit closer. We go 1 more standard deviation. You will cover, in this range, let's do it this way, we'll cover 95% of the data. We go 2 standard deviations out. Okay, and then if we go 1 more standard deviation out, or 3 standard deviations, we will cover 99.7% of the data. Points. Okay, so 1 standard deviation of the mean covers 68%, 2 standard deviations cover 95%, and 3 standard deviations cover almost the entire data set, aside from some outliers, okay? And so what we're doing here essentially in 12.4 is we are answering questions to demonstrate whether we understand 1, 2, or 3 standard deviations out. So most of your questions are going to revolve around your understanding of 1, 2, or 3 standard deviations out. Let's see if you can answer some of them. And we already did a couple, but let's start out at the beginning. The scores on a test are normally distributed with a mean of 70 and a standard deviation of 14. So a mean of 70, that means that if we're looking at this, let's take this and put the 70 right here, right? So that's your mean. And a standard deviation of 14, that means every standard deviation up or down, each step is 14. Does that make sense? And it can change. The mean can change for every problem. The standard deviation can change, and you guys learned that from section 12.3. Okay, so 1 standard deviation is worth 14, whether it's up or down, all right? What is the score that is 2.5 standard deviations below the mean? Let's look at the data. So 2.5 is key, obviously it's standard deviations, and the other thing is below. That's key. How do you answer a question like that? It's really easy. You have to take your mean, right? If we want 2.5 standard deviations, what are we going to multiply 14 by? What does 14 get multiplied by? 2.5. That's it. 2.5. And since they say below, what are we going to do? Subtract it. That's it. Done. Somebody give us the answer. What was it? 35. And that's it. Done. So a score of 35, in this case, we'd be a 70 here, 1, 2.5. The 35 would sit somewhere in here. Not quite 3 standard deviations out, but 2.5. Does that make sense? Okay, it'd be on the left side of your data set. All right, let's take a look at this next one. The scores on a test are normally distributed, meaning that we can follow this general model. If it's skewed to the right, like this graph is this, or skewed to the left, this doesn't apply. But when it's normally distributed, even, symmetric, about the mean, you can apply that, and that's all we're studying over here. So we have a mean of 100, there's your starting point, right? We're going to add or subtract off of that. Standard deviation of 30, meaning that 30 is going to be a key player in what we do, right? Find the score that is 3.5 standard deviations, meaning that we're going to multiply 30 by 3.5. Above the mean, meaning that we're going to add. Does that make sense? Somebody have an answer? 205. That means that our mean is 100. 1, 2, 3.5. This one is very much an outlier. It's probably at the very top of it, meaning that, let's say that this is, I don't know what 205 might be. The height that this, I don't know, rocket could go to, 205 miles, I don't know, whatever it happens to be. That is an outlier, very much an outlier there, okay? Does that make sense? Okay, let's take a look at this next one. The scores on a test are normally distributed with a mean of 30 and a standard deviation of 6. So you should lay out your 30, standard deviation of 6. You know you're going to do something with it. Find the score that is 2.5 standard deviations. Now they actually write it out this time, but does that matter? No. What are we going to multiply 6 by? 2.5. And it says below the mean. So subtract. Answer? 15. Done. And you can picture what that would be on your normal distribution. Okay? And you can see on this that that's exactly what's going on here. Well, if it wasn't so blurry. So here is the number of cars that were, number of car buyers. Here's the price of a new car in thousands of dollars. So as you can see here with this car, or the number of car buyers in it, it is normally distributed. With it, the mean is clearly 23,000. So why don't we read it? Not everyone pays the same price for the same model of car. This figure illustrates a normal distribution for the prices paid for a particular model of a new car. The mean is 23,000 and the standard deviation is 2,000. Sure enough, take a look here. The mean that goes right down the middle here of our normal distribution is 23,000. We have a standard deviation of 2,000. As you can see, here's our mean, 23,000. 2,000 up, there's 25,000. 2,000 down, there's 21,000. 2 standard deviations, there's 27, and there's 19. 3 standard deviations, and I'm going to erase this now. 3 standard deviations, you're at $29,000 for the price of a car, and $17,000 for the price of a car. Okay, so what does this mean? Sure enough, this matches our data. What it's saying is within 1 standard deviation of our mean of 23,000, you get the majority of your car buyers. Then 2 standard deviations, we get almost all of them. 95% of car buyers will fall within the range of 19,000 to 27,000. Does that make sense? And then 99.7, all except a small 0.3% of car buyers will be able to purchase a car between 17,000 and 29,000. Does that make sense, guys? And this is an actual application of what we're doing. Okay, so you can see what's going on there. Let's actually go and answer the question, all right? So, here's the question. The percentage of car buyers who paid between $19,000 and $23,000. Okay, so the percentage of car buyers who paid between 19 and 23. How would we go and figure that out? So we know this is the mean. They want the percentage of car buyers that fall there. If we know that from here to here, one standard deviation of mean is how much? 68% of them. Then we can actually determine how much this piece is already. How much is that piece? If we know from here to here,
34.
Exactly, 34%. Does that make sense, guys? And if we know from here to here, 2 standard deviations is how many? 95%. If we have 4 slices here, what can we do here? Yeah? So how many?
Can't you just divide 95 by 2 and that give you the 19 to 33?
Yeah, you could do that too. So there's lots of ways to do it. So the main way is I wanted to show you how it all was in pieces, right? So now that you get it, let's just double check. So divide 95 by 2, what do we get?
47.5.
47.5. So this should be 47.5. Now, if we divide this in 4, what is this small piece here? 23.75? Okay. So now, question. Do we have a match? No. Not quite. But, let's go with what you guys said, shall we? So, we know that this is 95%, right? And so we're looking for half of that. Everybody agree? So this is going to be half of the 95, which is, one more time? 47.5. Okay. Good job. All right, so let's move along. Let's do another one. And so they start calling this the 68, 95, 99.7 because that's each of the standard deviations. And so let's go answer more of these questions. All right, so here we go. Price of a car, you may not be able to see it here. It's really, really tough to see. So maybe I can zoom in one more time and you know that it's following the normal distribution. So this is 12,000, 12,500, 13, 11,500, and so on. So it says, what percentage of buyers paid between $10,500 and $12,000? So 10,500 is right here, and 12,000 is right here. This is the mean. If you can't see it, it's the mean. We know that this is 1 standard deviation, this is 2 standard deviations, and this is 3 standard deviations out. Does that make sense, guys? So, if we know that this is 3 standard deviations out, how can we calculate this part of the graph? What would we need to do? Exactly, it's half, because 3 standard deviations would be 99.7. Does that make sense, everybody? 3 standard deviations out is 99.7% of the data, because they asked for 10, 5 to 12, which is half of it. So if we take half of that, we'll know the answer. What's the answer?
49.85.
Oops. There you go. Wait. Did it get it?
Yes.
Oh,
It's just
it did.
another.
Wait, no. Yeah, it did. I don't know why I skipped that. All right, good. Next. Does that make sense, guys? That was good. Okay, let's move along. Shall we? All right, so next one. What percentage of buyers paid between $11,500 and $13,000? This is actually the same exact question, so I'm not going to do it. It's going to be the same answer. Okay. Take a look at this next one. Okay. Use that rule to find the percentage of buyers who paid more than $25,000. More than $25,000. Do you guys see what that is, right? More than $25,000. Well, we know that from, here's your mean, right? If that's your mean, here's 1 standard deviation, 2 standard deviations, 3 standard deviations, right? If that, all that, is 99.7 on both sides, and that's a key piece, both sides, what is this little piece right here?
0.3.
Almost.
0.2. 0.1.5.
There you go. Because there's another sliver over here. Everybody agree? This sliver from both sides is the 0.3. Everybody agree? And so if you want to know half of that, then it's going to be half of the 0.3 or 0.15. It's got to be 0.15. Okay, does that make sense, guys? Okay, very good. Okay, let's move along. All right, so it says the scores on the graduate record examination, this is the test to kind of, it's like the SAT for getting into grad school, are normally distributed with a mean of 590. Okay, let's just record that. Standard deviation of 111. Okay, use the 68, 95, 99.7 rule, but they don't have a picture for you, right? But you kind of get it so far, so let's see what we can do. Rule to find the percentage of people taking the test who score between 257 and 590. Use that rule to find the percentage of people taking the test who score between 257 and 590. Well, this no longer is asking for what's 1 standard deviation out, 2 standard deviations. So how would we figure out this one? How would we figure out the percentage of people taking the test, knowing that if we go 1, 2, 3 standard deviations out, we can figure out the range? Why don't we just draw a picture of what's going on, shall we? So here's our situation. Oh boy, not that. Let's try this again. Okay, so we have our mean. Our mean is 590. Everybody tell me what is 1 standard deviation out from 590 in both directions. It's 111.
479 to the left.
479. And then what? 701. Okay, good. So that's 1 standard deviation, right? This covers 68% of them. Agreed? Okay, let's go another one. What is 1 more standard deviation out?
368.
368. Other end? 12. All right, 812. Let's go 3 standard deviations out. 923 and bottom end? 257. Okay, there it is, isn't it? In other words, what are they asking for? They're asking for the percentage between 257 and 590. In other words, they're asking for what?
368 and 470.
They're asking for the percentages. So they're asking for what? Half to there. Does that make sense, everybody? And there it is. They're asking for half of what? Are they asking for half of 99, 95, 68? The 99.7. Because we're 3 standard deviations out, this 3 standard deviations is the 99.7 range, but they only want from 257 to 590, meaning that they only want half of that. What's the answer? 49.85. And some of these numbers will start to look very familiar. It just depends on the situation. Okay? Let's take a look at this next one. Scores on the GRE are normally distributed with a mean of 553 and a standard deviation of 143. Use that rule to find the percentage of people taking the test who score above 982. Well, let's go look at it again, shall we? So, above 982, we have a mean of 553. Everybody agree? One standard deviation would be what? 696. And here's the thing. Pause for a moment. They want to score above 982. Do we even care about what's below that? No. What's the next one? 893. So 2 standard deviations out, not there yet. 3 standard deviations? 982. In other words, they want the outlier, don't they? Because they want the number who score above 982, meaning that they want this little sliver piece. Is that 0.3? No, we learned it's what? 0.15, because both of these on the outside are 0.3. So if you want the score above 982, you want half of that. So that's 0.15. There it is, 0.15. Good. All right. Let's take a look at this next one. Assume that a normal distribution of data has a mean of 14, okay, and a standard deviation of 4. So we have a mean of 14, SD4. Use that rule to find the percentage of values that lie above 2. Okay, let's take a look here, and let's just start with a new one, shall we? So here it is, and here's your mean, right? Standard mean of 14, standard deviation of 4. So it says above 2. That means we probably need to go back here for a little bit, right? So 1 standard deviation through here is going to be what? 10, right? Because it has a 4. Another standard deviation, 2 would be? 6. Another standard deviation would be? 2. And then we get into that little sliver piece, right? So if they want the percentage of values that lie above 2, they want everything from here, including that little sliver over there, don't they? They want everything. Meaning that, what's the one little piece that we need to take out of the total to find the answer? What piece do we not need? No. This other little piece right here. This is what you don't want. We want everything else. Does that make sense? Everything above 2, meaning that from here all the way down, 3 standard deviations plus that little bit. How can we figure that out? How much is this worth? 0.15. This little piece is 0.15. We want everything besides that, so what do we do?
Subtract 99.7 minus 1.15.
Almost. No, there's definitely...
95%.
No. What is this total, actually? 100%. If you take the whole thing, all 100%, and we want everything besides that, what do we do?
Subtract it from 40,
or subtract 0.15 from it. Does that make sense, everybody? Because you're trying to figure out how much of your data, all 100% of it, is not that. Does that make sense, guys? These little extra pieces make up the last 0.3% to make 100%. So as a result, if we want to know everything above 2, we want all 100% minus that little piece, and so it should be what? 99 point? There we go. Okay. So 99.85. Okay, and so we now move on to z-scores. They're not very difficult. I just want to use the help me solve this to show you guys that you can find stuff as well, just in case you forget this. Z-scores are a pretty easy topic, and let's take a look at this. It says a set of data items is normally distributed with a mean of 150 and a standard deviation of 20. Convert 150 to a z-score. And I'll explain what this means in a moment. So let's just go through and look at the help me solve this, okay? So a set of data items is normally distributed with a mean of 150 and a standard deviation of 20. Convert 150 to a z-score. All right, so let's read through this real quick. Computing z-scores. A z-score describes how many standard deviations a data item in a normal distribution lies above or below the mean. The z-score can be obtained using the following formula. Your data item minus the mean divided by the standard deviation. So the data item minus the mean divided by the standard deviation. That's really important for you to have. So I'll just put that here. So your z-score is your data item minus your mean divided by the standard deviation. Or in other words, your value for x. You can say x minus x bar over SD, right? Because x bar is your mean. Any data item is your x value divided by your SD. Okay? All right? So, with that said, data items that are above the mean will have positive z-scores. Data items below the mean will have negative z-scores. The z-score for the mean is 0. So just as an important note, the relationship of z-scores to our normal distribution. A z-score that is at the mean is going to be 0. A z-score for a data item that is above is going to be positive. The z-score for a data item below the mean is going to be negative. Okay? So let's continue onward and do the one for this one. So we compute the z-score for 150 by using the following formula. And you can see it right there, z of 150. And so let's go do that. Notice how they use a little subscript there. So you might want to do z subscript of whatever data value you're looking for. Okay? And so as you can see here, 150, let's look at this. Data item is 150. Your mean happens to also be a 150. You can already see where this is going, right? Divided by your standard deviation, which is what? You should have gotten 0 for that one. Does that make sense, everybody? They just happen to use one that is going to be 0. So then subtract it, okay, and the answer is 0. Okay, so anyways, let's go do this next one. Okay, I just wanted to go through that to show you. And like I said, z-scores are really easy. So let's take a look here. We want a z-score of 136 because they said convert 136 to a z-score when you have a mean of 120 and an SD of 16. So what do we know? We know that your z-score of 136 is going to be that value minus your mean divided by your standard deviation. We already know that this is going to be a positive z-score because our value lies above the mean. Okay? Anybody got a value for this? This is going to be 16 over 16, which is 1. Okay? that easy. Let's do another one. As you can see, it's super, super simple. All right, so set of data items is normally distributed with a mean of 80 and a standard deviation of 7. Convert 86 to a z-score. So 86 is your data value. Sure enough, it's reflected there. Minus your mean of 80 divided by 7. What is that? 6/7? Do not round to the final answer, then round to the nearest 100. Somebody got an answer for that? 0.86. 86. Good. That's it. And we know that this lies above the mean because it's positive and your value was already above it anyways. Okay? I'm going to skip all this. I'm going to skip that. Let's skip that one, same thing. Let's see here. This is the same stuff, just in context, so we might as well do it. Let's just go knock this one out. We're pretty much almost done here. Scores on a dental anxiety scale range from 0 to 20. 0 being no anxiety and 20 being extreme. The scores are normally distributed with a mean of 11. Okay, that's important. SD4. Find the z-score for an anxiety of 17. Okay. Should our value for our z-score be positive or negative, just from looking at this? Should our z-score be positive or negative? Without even positive, exactly, because 17 lies above the mean, right? So our score is found by taking 17 minus 11 and dividing it by 4. That's going to be 6/4, 3 halves, 1.5, right? I mean, you guys could have done that on a calculator, no big deal. So there it is, 1.5. Bottom line is that really very tough? No, it's not. Piece of cake. Okay, I'm going to skip number 16. We're pretty much done. It's all the same stuff. Does that make sense, guys? Okay. So this is the last question I want to do for the semester. It's number 18. And this is where z-scores are really valuable because they help you compare two things. All right, let's take a look. This is a very valuable problem because up until this point, you're like, well, what's the point of having a z-score? Okay, let's look. Intelligence quotas on 2 different tests. This is really important to consider. Okay, this is what I'm going to talk about in a moment, are normally distributed. So I give this side of the room one test. I give this side of the room a different test. Okay, the scores for both, when I take the scores from this side, separate, and the scores from this side, separate, they're both normally distributed. You with me so far? Meaning that we can compare the two. If one is skewed and the other is normal, we can't. But they're both normally distributed. Okay, that's what this is saying. But I gave 2 different tests. These guys over here got a different test from you guys. All right. Test A has a mean of 100. So the mean is 100. You with me so far? And a standard deviation of 12. Okay? Test B has a mean of 100 and a standard deviation of 13. Okay? Use z-scores to determine which person has the higher IQ. An individual who scores 126 on test A, or an individual who scores 130 on test B. Now, this is where you need to pay close attention, because this is why z-scores are valuable. Because you want to compare to see, okay, somebody over here, they scored a different score on a different test, but we can compare the two. Does that make sense? Even though this has a higher score, it may not necessarily mean that this person is smarter, or not smarter, has a higher IQ than this one. Does that make sense, guys? And that's where the value of z-scores come in, is the ability to compare across different scenarios so long as the data is normally distributed. Okay, so let's take a look at this. So this is 126 minus 100 over 12. Did somebody get that? 2.17. Now, if this one is lower, if this z-score is lower than this one, then this person has a higher IQ. And vice versa. So here's 130 minus 100 over 13. What was that? 2.3. And so what this allowed us to do was basically get everybody on the same playing field, even though they took different tests, so long as they're normally distributed. So we can conclude that who has the higher IQ? Person, yes, B. Does that make sense? And that's it. Okay, that is all for this semester.